method to extract from the market a multivariate risk-neutral distribution. So when you have a cross-section of European options on one underlying, then it's quite well known that you can extract the risk-neutral density, and this one is actually unique if you have infinitely many strikes. And so usually if you have a good number of strikes, you can actually get a good estimation of the risk-neutral density of the underlying. But this is in the univariate case. Now in the multivariate case, there are very few methods, and then a lot of people rely on assuming a model or, yeah, that's mostly assuming a model or the mixtures of model, but like there are very few approaches that try to get a model-free approach to really get the multivariate risk-neutral distribution. And so what we do in the paper is construct one model that is consistent with all options on a set of individual assets, and also all options on basket options that are linked to these individual assets. So we could really consider some cases where we know not only basket options on, let's say, 5 assets, but also spread option between these assets and different basket options with different weights. So we are able to add a lot of constraints as long as they come like linear combination of these individual assets.
Sorry, basket options or options on basket options? Because you wrote
options on indices. So options on baskets. Yeah. Yeah, yeah, indeed. Option indices. So in one dimension, so I'm just recalling how you would get the risk-neutral density. So this is quite well known. If you have the price of a call option, you can write it this way, like the price of the call is related to the density of the underlying under the risk-neutral probability. And actually, you can extract this density by differentiating twice with respect to the strike. And so that allows to get risk-neutral density in one-dimensional world. And now we want to actually do this in a multivariate setting. So what do we know? What do we assume that we have access to? We assume that we have access to marginal distribution of D assets. So we have options on these D assets. Enough so that we can estimate using, for instance, this approach, we can estimate well the marginal risk-neutral densities of these D assets. And in addition, I assume that I actually know also the distribution of indices or baskets. So that's where the confusion comes. So baskets that are linear combination of this x1, x2, xd. And I assume I have some linear combinations, so I have k of them. So k is going to be my additional constraints compared to the original problem where you're only interested in getting x1 or xd. So now I want a multivariate distribution. So I'm trying to include information I have from the market on this multivariate distribution. And this information comes from the distribution of these indices. So anytime you have options on indices that are traded, and if there are enough options on this index, then you can extract, using the previous method, the univariate method, you can extract the distribution of this index. So that gives you, in fact, information on the dependence. Because now the distribution is a distribution of a function that depends potentially on the D assets or on a subset of these D assets. So, for instance, you could think of Microsoft that would be a constituent of several market indices, and each of these market indices has a lot of options that are traded on this index, and so we would be able to get this distribution. So there's the Dow Jones, the S&P 500, 100, the NASDAQ, the S&P sector, technology sector. So all these indices would include this xi and would be different weights potentially. But, and so that are the constraints. How do we do that? We have a combinatorial algorithm, so this is just a numerical approach. And based on this numerical approach, we give one model. Actually, we could get several models because it just generates one model. And all of them have some properties that we hope are sensible and make sense in practice. So it builds on a previous paper that for people who have come to my lecture on the mini course, there has been extensive discussion on this block rearrangement algorithm and how to implement it and its properties. I'm going to recall some of them here, but if I go too fast, then you should listen to the Sunday's lecture. and so we built on this block RA, and the block rearrangement algorithm was developed to only include one constraint, a constraint that is based on, I know the distribution of the sum of the indices, of the individual assets. And now, actually, we call this the constraint BRA, where we add a set of constraints. So now we have K distribution of weighted sums that we actually include. So what is this block rearrangement algorithm? Quickly, it builds on an algorithm that was at the beginning developed to minimize the variance of the sum of random variables. So it was outside the finance world, more into the statistics world, where the question was just, I know margins, I'm looking at the sum, and I want to know what is the dependence that minimizes the variance of the sum. And there is one way to do it that was developed, a numerical method, which consists of discretizing each of these D distribution into a matrix. So Xij is for x1, for x2, and for xd. It's just discretized value, all equally likely, in each column. And then each column represents the distribution. And we represent the multivariate distribution, so you have to see this matrix as a copula. So this is actually your multivariate distribution. You have access to the margin as the columns. And the way the columns interact with each other is the dependence between the different variables. So if they are, for instance, fully comonotonic, fully positively dependent, they would just be ordered in the same, like from the smallest to the highest, and they would all be comonotonic. And that would be one possible dependent, one possible copula. If you make them independent, so if there's no specific order, then you would have another dependence. But really, the distribution, when you look at the matrix, that's your full model. That's your multivariate distribution. That's just a representation of a copula in finite dimension. Finding the rearrangement that actually minimize the variance of the sum. So the sums, you would just sum over the rows, and you would flip the values in each column so that to minimize the variance. And this is NP-complete problem, because if you, it means that there's no polynomial complexity algorithm that can solve the problem. There is an algorithm that works really well and is a very good heuristic, which is the rearrangement algorithm, and was developed in 2013. Very simply, you take every column, each column one by one, and you notice that when you take one column and you make it as negatively correlated as the sum of the others, you actually decrease the variance. So you have an algorithm then that at each step, you start from a matrix, you take one column, you make it negatively correlated with the sum of the others, and the sum of, the variance of the sum is actually decreased by this process. And then you do it with another column, with another column. At each step, you decrease the variance. So at some point, you converge and you stop. So that's the algorithm, the very simple interpretation of the algorithm. We extend it a bit, and then actually it's an extension that's really needed if one wants to extract the dependence, because it helps to get a more precise value. So when you do this, what you do, you really take one column and the others together. And you just use the fact that the variance is minimized when the correlation is as negative as possible. But correlation is a notion that works well in 2 dimensions. So you take one column and the sum of the others. One thing that you can do is just split your D columns into 2 subsets and just take a partial sum anti-monotonic with the other partial sum. So that's exactly the idea of the block rearrangement algorithm, where we look at partition of our D column into 2 subsets. And now what we do, we sum over the one subset, we get S1. On the other subset, we get S2. And we make sure, when we look at the variance of the sum, it's actually minimizing the variance of S1 plus S2. And to do that, we just have to make the correlation between S1 and S2 as negatively as possible. So it means rearranging the matrix so that all the rows that correspond to S2 are put in opposite orders to S1. And then when you do that, you can do that for every partition in 2 blocks. And then each time, you decrease the variance. So you go closer to your objective. Ideally, you converge. And the ideal solution would be when all the row sums are exactly the same, and then the variance is exactly equal to 0. And so why this algorithm that minimizes the variance helps to infer dependence and solve the problem that I presented at the beginning? Simply because if you look at the problem with one constraint, so imagine that you know the sum of the distribution of the sum, so you have only one constraint on this. And you write now in the matrix x1, x2, xd, and here you put minus the discretized value of s. Finding a dependence among the d variables that is consistent with this sum is actually finding the order here, so that when you add x1 plus x2 plus xd, you get exactly si, so the opposite of the last column. So we are actually trying to get x1 plus x2 plus xd plus 1, not our last column, equal to 0 identically. And if we manage to get 0 as a sum everywhere, we have obtained an equality almost surely. So we are actually finding the distribution such that x1 plus x2 plus xd equal s almost surely. And of course, then we have also equality of distribution. So we have a very strong statement as soon as we get 0 everywhere. In practice, because of the discretization, you will never get exactly 0, but you'll get things that are like of the order of 10 minus 5, 10 minus 6. So it will be very small, and actually you will very closely, statistically, you will not be able to reject the distribution that you find here between x1, x2, xd will be actually the distribution of the sum, will produce the distribution of the sum that you want. Now, this block rearrangement algorithm is good. It allows to find one possible dependence such that it's consistent with marginal distribution of the sum. It does the job. And at first, we thought we could get like this all possible distribution because we had the impression we were not making any specific assumption. We were just randomly picking the partition for applying the block RA. We were randomly applying it on the matrix. But still, what we notice is that every time we run the algorithm, we go close to a solution, which in the normal case corresponds to maximum entropy, corresponds to a solution where you maximize the determinant of the correlation matrix between the d variables. So this is one point that we have proved numerically, and we are not able to prove in theory. But it's a nice property in the sense that maximum entropy is often what the nature is doing when you don't constrain it. So if really the only information you have is marginal and sum and nothing else, then the most plausible model should be the maximum entropy one. So it's not completely absurd to take the output of this algorithm. And then what we did, so this is a small example to show you if you have trouble to see what you get from the block RA. To show you what you get actually as output. So if I put as input 2 normal distribution, and the sum, I also assume that it's normal. I choose sigma s so that the implied correlation is 0. I run the block RA. So really what it means putting x1 being the discretized normal, x2 discretized normal, and the sum discretized normal. And I put them in random order, so you could just put them in even increasing order if you want. So you start from one situation, you apply the block Ra, and then what you get is that the columns are going to rearrange themselves using the rearrangement algorithm. And when you extract the dependence, it's actually independence. Not surprising, because the implied correlation is 0, and actually the independence is a possible dependence that would explain such a situation. And so that's the joint distribution that you get on the normal scale. If instead you take a volatility for the sum that's much higher, again, not surprisingly, you are actually going to find the bivariate normal distribution. So the algorithm is going to rearrange x1 and x2, and when you plot the output, dependence output from x1 and x2, you actually get the copula for a bivariate normal, or you could see it, the bivariate Gaussian on this scale. And then, if instead of taking a normal, you skew it, and you take a skewed normal, what you get is actually that you can't have any more symmetric dependence, but the algorithm is going to have to work on x1 and x2 and change the dependence so that when you sum them, you reproduce the skewness of the sum. And what we find is that the algorithm is going to find tail dependence on the left corner to allow for to explain the skewness in the sum. So really, the algorithm gives you a dependence that's consistent with that. And this is only when you put one constraint, which is one sum. Now, the idea is to have more than one constraint. So assume that you have now several weighted sums that are available. The idea is exactly the same, is to actually discretize these k constraints with the same trick, and then to consider a bigger matrix in which you put the d-dimensional vector that you're interested in, and each other column, k additional column, that corresponds to your k constraints. And now you work on this very big matrix so that you decrease some variance, because actually the operation I'm going to do on this big matrix are always taking a block, making it anti-monotonic to another block in order to create, to decrease the variance of something. And so I need to formulate the problem as like using variance. And then you can actually reformulate the problem by looking at this big matrix, saying that each constraint can be seen as a weighted sum of the d first column minus one of the constraints. So this L cap pi corresponds to each of the constraints. And if you find that this v is equal to 0, you actually satisfy exactly that all S1, S2, and Sk have the correct distribution. And so ideally, you want all these variants to be equal to 0, which means that each constraint will be equal to 0. If you like one constraint more than another, you can actually weight the output so that you'll try to minimize. And apply the constraint block Ra that I haven't put the details, but is really just putting, like thinking a little bit more how you choose your blocks. But it's the same spirit. And practically, we try to minimize as possible this objective V. Two possible situations can happen. The first one, that's you're lucky, or that's the market is nice. All your constraints are satisfied. So now you find a model that satisfies all your margins, so it's consistent with options on individual assets, and also options on all the sub-indices that you have put inside the machinery, inside the constraint. And then you can price anything using this model. So that's, and this price is kind of model-free because we have made no assumption except that taking into account the marginal distribution that are given from the market and that are extracted in a model-free way. Second situation, the linear constraints are not compatible, and then that means actually that we've added marginal distribution from the market. So imagine you have options on the Dow Jones, option on S&P 100. They give you prices, they give you distribution for the Dow Jones, for the S&P 100, But these two are not compatible. They create an arbitrage. And so this output matrix gives you a distribution which cannot explain all the distribution in the market. So it means that somewhere there is an arbitrage. So now we haven't worked really to find, like, we are able to say options are inconsistent. We are actually not, we haven't worked yet on finding the arbitrage. No, it actually doesn't find a model. There's no model that would satisfy these constraints. So it's not no maximum entropy model, it's just no model. Because if there is a model, then the algorithm would actually find it. And so we've done some examples that are, for instance, very toy model. We haven't done empirical example where we take 6 normal distribution, we constrain them on the first 4 and on the last 4 we have, and also on the total sum. And then we run the algorithm. And when you run the algorithm, you find that the V is, so this is of the magnitude of 10 minus 4, and is distributed over that. So each time you run the algorithm, it has been run m times m being 1,000. So 1,000 times we run the algorithm, and we find that it's always close to 0, 10 minus 4, always of the order of 10 minus 4. And the correlations that are extracted from the market, from the model, are correlations, so row 1, 2, row 1, 3, all the correlations are displayed here. And you could see that this 1,001 of the algorithm don't give always the same correlation, but gives you some range. So there is it's not exactly the maximum entropy one, it's just around this maximum entropy one. And you have some range of possibilities. If you are in an incompatible constraint set, and so that can happen if, for instance, you constrain, in this case, the sum of the first 4 to be normal 0, 6, and it was normal 0, 10, 10 and 24. If you put 6, now the 6, 6 and the 24 is too big, so it starts to be incompatible. Then what happens is like the algorithm tries to converge, but V at the end is not of the order of 10 minus 4, but is like 0.1. And actually, it means that there is one constraint at least that is not satisfied. And now you could see that we really get into a corner solution because the correlation that we get are really just extreme, like 1, 1, 1. And especially, whatever we run 1,000 times the model, the algorithm, and it always gets to the same, gets stuck in the same point where we get this corner solution, which is the best solution, that is the closest to explain all constraints, but that cannot explain all constraints. So we haven't done any empirical application with more than one constraint. There's one empirical application that I started to present last year, and then we've done a lot of progress on it, which is to explain the correlation with premium. And so we do the methodology, we apply it with the 9 sectors of the S&P 500 and the S&P 500. So it means that we have a 9-dimensional problem with only one constraint, which comes from the distribution of the S&P. You could see it as the weighted sum of the 9 sectors. And we are able to show that the dependence that we find between these 9 sectors is non-Gaussian, time-varying, very asymmetric. And we are able also to find some toy model to explain the market. One thing that we were able to do is really to look at the dependence, the multivariate distribution, and explain that this asymmetry that we find comes from the copula, from the dependence, and not from the properties of the margins. And we give a small model that can explain some asymmetry that we show in the paper, which is simply modeled using 2 parameters skewed normal copula, which already explains a lot what happened in the like to model this 9-sector of the S&P. So to conclude, so we develop a novel algorithm which is consistent with maximum entropy when you have one constraint. Actually, we haven't proved anything with more than one constraint, so this is also one thing that I'm not sure it actually is still consistent with maximum entropy. And we developed some application. One is getting a good multivariate model to price, which is what I presented here. And we hope to be able to use it for detection of arbitrage opportunities and understanding also what is the effect between volatility and dependence. So when you have changes in the prices of indices or changes in the distribution, are they driven by changes in volatility, so marginal effect, or are they driven by dependence, changes in the dependence? Is it skewness in the margins, or is it skewness in the dependence that can explain the distribution that you observe? And then there's probably some application also in optimal portfolio selection when you try to extract information from options to get a better portfolio choice. So thank you very much.
Thank you, Carole.